All right, well then, if you would, please get out your hydrolysis notes that you've already copied into your spiral, and we'll tackle the end of this unit. Good news about today is more than 80% of what we will do is exactly what we've already been doing for the last 2 lectures. I just have a tiny twist to sprinkle in for a different type of substance that we haven't discussed yet. We know so far that we can be given a strong acid or base or a weak acid or base, and we know how to analyze pH type calculations based on that given substance. Well, there's a third substance that we need to understand has a slight difference, because salt is harder to immediately look at and know what it was going to do to a pH when it's added to a solution. So you're going to want this right here on this first slide kind of near you as I go through the first couple of examples, because it's going to help clear up a couple things about salt. But let's just start off by making sure that we understand what our focus is. Salt, by definition, is any ionic compound. So it'll be essential that you can be given a substance and know it's a salt right away by saying, okay, it's a metal with a nonmetal, ionic, salt, or it's a polyatomic bonded to anything. These are review vocab that you should definitely already know. But those are some of the ways to identify a compound as salt. So here's another thing that you know about salt in terms of its origin. Salt is created through a neutralization reaction. We covered that in review on Unit 2. We know that if an acid reacts with a base in neutralization, it produces salt and water. So there's the salt. So what that means is the parents of a salt substance are acidic and basic. Our job to determine the impact on pH of a salt added to solution is going to be to go back and investigate its parents, all right? Figure out, did they meet during spring break? Do they still like each other? That kind of thing. And the strength of the parents will determine the impact of the salt. So I'm going to show you what I mean. The next couple slides are kind of messed up in the way I've decided to teach this. I don't usually do that to you, but the slides are not going to completely follow what I'm about to say. But this first example is here. Let's look at sodium chloride together. All right, so this might be the most famous salt, because usually if I say salt, you think of table salt. But remember, there's thousands of salts, any ionic compound. But the question I'm trying to figure out is, what would happen if I added him to water? What would happen to the pH of the water if he was added? So let me show you how to find the parents. If he was made through neutralization, an acid and a base, then I know that the determining substances there would be a basic substance, hydroxide, and an acidic substance, hydrogen. I also know that these parents would have been connected through an electrical charge, because that's how an ionic compound is built anyway. So I could look at the oxidation state of sodium and chlorine and look at their respected charges. To find the parents, I just need to connect the opposites. So one of the parents, if you connect the minus to the plus, is sodium hydroxide. The other parent, by connecting the minus and the plus, is hydrochloric acid. Questions on how I found the parents? Now, with your understanding of weak versus strong, which you should definitely be good at by now because we've done it so many times this year, I can figure out the impact of the salt itself, because I know that sodium hydroxide is a strong base because it's an alkali connected to hydroxide. I also know that hydrochloric acid is a strong acid Because it's binary, I bring clay. Look back in your slides. What pH impact is NaCl going to have? 7. Overall, no impact, because your slides say that if the parents are strong, it'll overall have a pH of 7. Let's do another one, but go slightly further in our analysis. I'm going to move around a little bit. I'm going to go to sodium bicarbonate, which looks like that if you translate properly. I know that it's salt because it's a metal bonded to a polyatomic, which is why this new idea of parent finding is happening. So let's look at the parents. The positive Na would be attracted to the negative hydroxide. The negative CO3 would be attracted to the positive hydrogen. I have found the parents. Is sodium hydroxide weak or strong? Strong, all right, we just used him in the last example too. Is carbonic acid weak or strong? It's weak, all right? There's a carbon there, or you could look at the H to O ratio. Both of those point you towards a weak substance. So if you added this salt to water, would you expect the pH of the water to go up or down? Ooh, they disagreed. Up. Because who won? The base. The base won, so I should be building a basic environment, and according to pH, the pH would need to be greater than 7. But let's take our analysis a bit further, because it turns out that if AP wants us to then look at quantities of like a molarity of the sodium carbonate, then we would need to be able to think a little harder. So start by writing this. Add to your notes that strong ions are spectator ions. Strong ions are spectator ions. Here's what I mean. When this goes into solution, the strong ion, which is the sodium, because he had the strong parent, will go into solution and do nothing. It'll dissociate and not change at all, which is the definition of a spectator ion. But the weak ion, in this case, the carbonate, because he came from a weak parent, all right, dad, am I right? Just kidding. Then he is going to change. He's going to undergo what we call hydrolysis, which is the name of the entire lecture today, because hydrolysis is what happens when a salt is going to alter pH. But it's always the weak ion that does it. Now, the word hydrolysis is going to point you towards a substance that we've already been interacting with nonstop, which is water. So the rest of this is going to feel very familiar once you are able to get through this new part. So let's take the weak ion, and I'm going to hydrolysize it by adding it to water. So I'm going to go, there's the ion. So all I did was I pulled the ion out of the salt, and I'm going to add it to water. Now, this will be Bronsted-Lowry as we expect it to be. The way I think about it, because I've seen y'all get confused here, is I already know that I am building a basic environment because I know my pH range. I know it's above 7. all right? I know that the base 1, so what substance should definitely be present as a product here? Hydroxide. Because the environment I build must support the pH being above 7. That's what hydroxide does. According to Bronsted-Lowry, that can only happen if a hydrogen, a proton is donated over there. And now I've written my hydrolysis equation. You try one. I want you to do ammonium nitrate. There's ammonium nitrate. I want you to do everything I just did. Find the parents, find the pH range, then write the hydrolysis equation. Take 2 minutes. So let's start by finding mom. The positive NH4 would have come or would have been attracted to the negative OH. And then dad, the negative nitrate, would have been attracted to the positive hydrogen. There's the parents. Is ammonium hydroxide weak or strong? It's weak, all right? You haven't memorized the weaks, but you know all the strongs. So we have a weak sample here. Is nitric acid weak or strong? Strong, you can tell by looking at the HO ratio. So right away, I can conclude that my pH range is going to favor acidic. Therefore, it must be less than 7.
For the NH4OH, is it always gonna have that OH for the first part, like when it's like that? I'm kind of confused. Can you explain why it's the OH right there?
because hydroxide is negatively charged and ammonium's positively charged, so they attract each other.
So that just comes from like nowhere, or where does it come from?
It doesn't come, it comes from the idea that we know originally to make the salt, we had an acid and a base react to form him. All right, so by going backwards, I know that the acid would have distributed an H plus, the base would have distributed the OH minus, and if I split the salt apart, I can guess who was attracted and with who.
Okay, yeah, I see it. Thank you.
Okay, so I know then that the strong ion, which is the NO3, will be a spectator ion. I know the weak ion, which is the NH4, will hydrolyze. So let's take the NH4 and add them to water. I am building an environment that has a pH less than 7. I'm building an environment that favors acids. That environment will include hydronium. The only way to Bronsted-Lowry hydronium is to donate from here to here. Therefore, here's your other substance. How did you do? As we apply this to real AP problems, the rest of what I could add, is only stuff that we've already been doing. All right, so the rest should be incredibly boring, which is, you know, kind of my style anyway these days. But what could happen is it would give you a salt, and you would need to do this. You would need to absolutely figure this stuff out. But then if it said, okay, well, what if the molarity is this? This is an initial concentration. Well, in that case, that reaction would be the R of a rice table, and you could fill in all the other stuff like we've been doing over and over and over again. So, as I mentioned, I'm a little crazy with the slides. We're going to skip this slide for now. We'll come back to that problem at a later time. But before we start, I do want to point out this summary slide that I threw into the middle here. I just want to stress what your mission is on next week's test for all pH problems. Because what they'll do is they will give you a substance to analyze. And your #1 job is to figure out what the heck you're looking at. Because if it's a strong acid or base, you just take the negative log and you're done. If it's a weak acid base, you'll have to add it to water in a rice table. If it's salt, you'll have to do hydrolysis, which includes parent finding, and then probably still add it into a rice table, depending on if it's the type of question we're about to do. So keep your mission in mind, and let's have some fun. This problem here is focused on sodium acetate. Sodium acetate looks like this. He is definitely salt because that is a metal bonded with a polyatomic, so that was the important part of identifying it. Now I say, oh, salt requires hydrolysis. I need to look at mom and dad. Mom here was sodium hydroxide. Dad will be acetic acid. Dad is an alkali hydroxide. Strong. Mom, did I switch those? Sometimes I switch places. Mom is a carbon-containing acid. Weak. I'll take the weak ion, the acetate, and hydrolysize him. So I'll go C2H3O2 as an ion and add them to water. I need to build a basic environment because it was the base that was strong. So I know there will be hydroxide. That H must have been donated away from the water to form that hydroxide. So that's everything that we've been doing today, which is really the only new stuff in terms of skills. But this problem wants a pH. It gives us a molarity. It wants us to do rice table type stuff. So I'm going to make that reaction the R in our rice table, and then we will get repetitive. Liquid water is ignored in a rice table. The given molarity here is 0.7. No product yet. Shift towards the zeros. I plus C is E. Make sure you stop me if you don't know where something comes from. As usual, we've got some bonus info here. It gives us a Ka. All right, remember what that stands for. It's the equilibrium constant based off of acidic data. And the Ka is 1.8 E negative 5. Do you see the issue? We have a problem. It needs to be basic. Now, this happened a couple times on Tuesday where the given data did not match the ion that we had in the reaction, all right, in order to help us find X. While it happens sometimes for weak samples, this mismatch will always happen for salts. It's an easy fix as usual, but don't forget to do it. Ka will only connect us to hydronium. We need Kb. But I know that Kw, the 1E negative 14, if you divide that by anything acidic, it gives you the basic version of it. Or if you divide it by anything basic, it gives you the acidic version of it. So if I take that Ka, or rather I start with Kw, all right, which is 1E negative 14, and I divide that Kw by Ka, 1.8 E negative 5, it will give me Kb. I get 5.6 E negative 10. Now, here is where we would normally just move forward to solve for X, which is what we need to do. You should do an unsubstituted equation because you're so sharp. I don't have enough board space. So I'm just going to go straight into subbing in the K value for the expression. Remember, it's K equals products over reactants. I know K. It's 5.6 E negative 10. So there's K equals the products, which are these two X's multiplying by each other, over the reactants, which is this expression here.
Mr. Cummings.
Yep.
But you know the 1E negative 14?
Yes.
Where did you get that from?
That's the constant value of Kw, which is connected to water, that you do not have to memorize because I will give it to you on the exam. They will give it to you on the AP exam. But this is Kw, and anytime you divide it by something that is acidic, it will give you an answer that is basic.
Okay.
We'll simplify here by cross multiplying, and I'll get X squared. You should distribute. It must be 0 equals. So keep the X squared positive and reverse the signs of the other items. And go to your solver. I had a student tell me last period that they still don't know what buttons to push to make the solver work. If you are a part of that problem, then email me. I'll send you a typed out pathway on exactly what to do. Don't let the solver issue be holding you back. The value of X for your quadratic cannot be negative, even if your calculator tries. We only care about the magnitude of this value in chemistry. So take the absolute value if it gives you a negative answer. I get 1.98 E negative 5 molar, which is the value of X, which also happens to be the value of hydroxide. So we've got some baby calculations left to do because that's a hydroxide concentration. The question specifically asks for pH. There's another mismatch here because pH is not connected to OH minus. KW helps again. KW divided by OH minus is H plus. So I could go 1E negative 14 divided by the OH of 1.98 E negative 5. And that'll give me the H plus concentration. Now I finally have a strong concentration of the H plus, which I know to get pH, I just need to go negative log. It's good, right? It's easy. Questions? I had a student earlier today ask me if the class was going to feel like this for the rest of the school year. No, it's not. We've got a bunch of non-math stuff second semester. Like, remember atomic structure? Remember, like, electron configuration, 1s2, 2s2, 2p6? Yeah, that stuff's good. What about just protons, electrons, and neutrons, or periodic trends? The further right you go on the table, the ionization energy goes up, and the further left you go, the atomic radius gets bigger. That's all waiting second semester. So, anyway. We're going to do one more problem, and it's the last problem that we'll work out together in this setting for this unit. So I hope that if you're getting stuck on something that you will speak up. Take a look at this last slide. Now, I want to point out the italices down here real quick. Please realize that K values are constant values, which means if you're working in a lab setting, not in this situation where you just have an instructor giving you questions, but if you're really doing chemistry, if you need to know the K value at a certain temperature for a reaction, you would just go look it up, right? You'd go to a big book or Google it or whatever. So the problem giving it to you is kind of less real world. Now the AP exam has to, because they're not gonna give you reference guides. But I just wanna point out to expect that when your college life starts. But I didn't give you the KAs on this last slide, and I'm not gonna make you go Google them now, so I will give it to you. Here's what we're gonna do. I'm going to give you a 7-minute head start on A. We're not gonna do B. I'm gonna give you a 7-minute head start on A to see how much you can get done without me. And then I'll swoop in and save the day, because that's, that's what I like. But the KA that you need for that problem is 3.5 E negative 8. So again, take the first 7 minutes, get as far as you can get. Let me know if I can help. If you're still, yes. If you're still rocking and rolling comfortably, then you can ignore me for the moment. But if you got stuck somewhere, you have questions, let's interact. We're looking at potassium hypochlorite, which is definitely salt because it's a metal with a polyatomic ion. So let's start with a hydrolysis analysis and parents. It looks like we've got potassium hydroxide and then HClO. Potassium hydroxide is strong. Alkali hydroxide. HClO is weak due to the HO ratio. The strong ion, potassium, will be a spectator. The weak ion, hypochlorite, will be hydrolyzed. So let's show that by saying, whoops, by taking the ion, adding it to water, I need a basic environment, which will be full of hydroxide. That proton would have been donated here to create the hydroxide. The problem wants us to do a further analysis, so I'm going to add that hydrolysis to a rice table. No liquid water in equilibrium. The problem gives us an initial concentration of 0.355. Nothing here. We're going to shift towards the zeros. I plus C is E. The information that was given at the beginning of the problem was this Ka value, but I see that I have a mismatch, as I always will in hydrolysis, with the OH minus product. So instead of a Ka, I need a Kb. So I'm going to divide Kw by Ka to get Kb. We should go unsubstituted from here, but to save board space, I'm going to plug into the equilibrium equation of Kb equals products over reactants. So 2.9 E negative 7 is going to equal the products over the reactants. Simplify by cross multiplying. Distribute. 0 equals. Keep the x squared positive and reverse the signs of the others. Another thing to watch out for on your solver is situations where there's so many insignificant decimals that it hides the scientific figure. Some calculators on this problem will require you to manually scroll to the right to find the E number after all those decimals. So make sure that you're careful and that you get the correct value here. In a happier world, the question would be asking for a hydroxide concentration, in which case we'd be done. While my lecture examples tend to not be that nice, some of the Schoology problems are. So make sure that you check what it's asking for so that you don't exhaust your work beyond what's necessary. But I want pH. This is a hydroxide. There's a mismatch. Can't get pH from hydroxide. So let's switch to H+. I prefer to do it by kW. You might have a different way. But I can go 1 E negative 14 divided by OH minus. And that will give me H+. I finally have a strong concentration, and I know to get a pH from that, it's simply negative log. You got it?
No, it's fine. It's fine.
I mean, I don't have the original number, but you'd be the first one to tell me I'm stupid. I mean, today, in the last hour. Just waiting on that text from my wife. No, I'm just kidding. I feel like sometimes they can hear me, but not you, and then they just think I'm sitting here talking to myself. What's he talking about? What's wrong with him? His depression is really showing. Okay. Questions, y'all. Questions, because this is kind of it. You've got 7 calendar days to make it so none of these steps mess with you. Please come see me in tutoring. They're all happening as scheduled. But keep in mind that there will not be a Zoom on Tuesday. You'll do your FRQ. There will not be a Zoom on Thursday. You'll do your test, and then you're going to eat a whole bunch of turkey and miss me a lot. I'm going to send you into your unit partners so that you can open up hydrolysis and get some work done with me around to help. So I'll be around to see you.
alcohol. Like, people are always like, oh, give me a sip of that. And I'm just like, oh, I don't really like the taste of it. So I've talked to him, and I'm just probably going to be the designated driver. So
Yeah.
I'm going to have to get used to dealing with really drunk people. I'm just going to be like, all right, cool. I'm taking you home. You're going to bed. I'm going to get you a glass of water before that, but you know.